Hi, and welcome to Zero Downtime Deployments, where we're going to take a look at application rollouts and rollbacks. I'm going to be your speaker. Hey there. My name is Chris. I am a consultant and advisor, and sometimes speaker. You can see some of my accolades there. So without further ado, let's get started. Controllers in Kubernetes are control loops that watch the cluster state. And if necessary, they're going to introduce some sort of change, right? So the control loop holds desired state. It's querying the cluster for actual state. And if those things don't match, then it takes action. So we're going to focus on the deployments and the StatefulSet specifically because they're primarily for long-running applications, and we want to look at their behaviors when it comes to rolling updates. So first look at deployment here. It describes the desired state for an application, right? So we're going to take the image that we want to run, the affinities and anti-affinities, all those things, and put them in the deployment manifest. And the deployment isn't alone in making sure that the application gets deployed. It's actually a wrapper for another controller called a Replica set, which enforces the replication factor. Replication factor is of pods, of course, and then within pods are application containers. But what that means is that if we create a deployment, then in a cascade, we're going to create the replica set, the pods, and the containers. And if we delete a deployment, we do that in a cascade as well. The rolling update feature that we get with deployments will change the actual state of the cluster to the desired state with zero downtime. Right? No client will be sent into any black hole. Right? That's the goal here. Deployments do support a wide array of application types, but really do have a feature set that works best with stateless apps. So pod host names are not really predictable. They have hashes that we can't really predict ahead of time. So talking to an individual or sending client traffic to an individual pod replica is a little bit more difficult. If you're going to embed a persistent volume claim within a deployment template for a pod, remember this is a template, right? You're going to have many replicas, and so PVCs typically have unique identities. I can't parameterize the name of the PVC within the template. So if I have it in read-write many mode, then that's great. Otherwise, well, that's what the StatefulSet is for, which we'll look at later. So replica sets are a top-level citizen in the Kubernetes API. Their primary job is really to reconcile desired state versus actual replication factor, right? So somewhere on the cluster, there are n number of pods actually deployed, and the replica set needs to reconcile that. So within the replica set object here, we see two important things: desired replicas, and then the label query. The label query is going to be used to do that reconciliation. And then when the answer comes back, a decision has to be made. Are there 7 pods? Great, do nothing, right? No action needs to be taken. If there are 6, then we've got to add a new one, right? Similar to kubectl run to add a new pod. If there are 8, then the replica set's going to kill one. And so this guarantees the availability of n number of application replicas across nodes in the cluster and across availability zones and such, right? They can be used independently of deployments, but if you do use them independently, they lose the rolling update feature that we're going to look at. However, there are some CD platforms like Spinnaker, which will use replica sets directly for other patterns like red-black. You will see them used in some cases. Now, the relationship between deployments and replica sets is typically a one-to-many, right? Where we've got a single deployment that's got multiple RSs underneath it. This is because an RS is a snapshot of an application version. So when we change the image, what happens is we hash the new manifest, and if the hash doesn't match the old replica set hash, then we create a new one and we roll out a new revision. Because we have this one-to-many relationship between the deployment and the replica sets, this allows us to roll out with zero downtime, right? So it lets us essentially increment the desired replicas of the new replica set and decrement the desired replicas of the old at the cadence that we specify. It also allows us to have n number of rollbacks, because if I want to roll back to an earlier version, I can just do that same pattern, right? And I've rolled back my application. It's also kind of lightweight tracking revisions of an app, so we'll look at the history feature as well. So the idea behind rolling updates is we're going to roll out those changes at the controlled rate, right? New pods are rolled out before old pods are terminated, because we want to have that new replica up before any of the old ones come down. Now the new pod doesn't go to the exact same node. It is independently scheduled and gets scheduled on a node that has available resources based on the resource request and other factors. And the default setting ensures that at least 75% of pod replicas are available throughout the update, right? So we're not going to tear down below 75% availability. You know, that's tweakable, that we'll look at in a moment in a subsequent slide. Client traffic is then load balanced across all available pods. As well, if you want to see the live in progress rollout, you can. Like anything else in Kubernetes, you can watch that for updates. So let's get to it. So I've got several node cluster here. So let's kubectl get node and see that we've got several workers that we're going to work with. So I'm gonna I've got a directory here of manifest that I'm going to use. I'm just going to cat the deployment one. So you can see we've got some settings here that will give us 10 replicas and give us some time in between the deployments for minimum ready seconds, and then also the default settings for max surge and max unavailable, which we'll talk about going forward. They're explicitly set here, but those will be the defaults anyways. And we've got a application here that simply outputs its IP and its host name, so that it will show us like which one is being communicated with from a client. So we will first set up a watch. And so in the interest of time, I'm just going to grab some commands that I've got going. So we're going to watch kubectl get pods, and then we're going to use the key value pairs here for the deployment. Right. So this is going to tell me no resources found, right? Because I haven't deployed anything yet. But let's go ahead and kubectl apply that. And we'll see that we've got 10 pods running. Now what I want to do is run a client on this other terminal here. And so I'm just going to run a client pod with busybox 1.27 so that I can run a loop. And so my loop is going to do a wget against the service. And what that means is I also need to create the service. So going back over here, we're going to expose our deployment. And the host info pod listens on 98.98, but we're just going to have the service listen on 80 to make it easy. So we expose that, and now I can run my loop. And what will happen is you'll see that it should query and see that we've got the certain RS hash, but we've got different endpoint pods that we're connecting to. Right? As we see change, we're going to see this RS hash change in each one of the requests. So we'll let that go. And so we've got our watches established. So let's introduce a change. So here we're going to set a new image that just uses a different tag. Same. So up here, host info latest, we're going to go to the Alpine version. And we're going to record that change so we can actually see it. And so let's take a look at the behavior that happens out of the box. So we get a number of new pods that are created immediately and one terminated immediately. And so most of our load balancing just right now is still going to the same pods, except for there's our first, I missed clicking on it, but there's our first request to the new set of pods. And then obviously we'll see that increase over time. So lots of change happening in the cluster, right? We've got a 25% surge and 25 unavailable. So we're going to see a quarter more pods each iteration through. And so there's some more terminations, cleaning up pods after they've been replaced with new ones. And so now all of our requests are going to the new set of pods based on the new hash, the 566 hash over here with our client. Right. So now let's look at undoing that, because let's say, we don't want this version of the application, something's wrong with it. So we're going to undo that. Now in this case, we're going to do an undo, but also get the status so we can actually see the watch as it happens, right? And see how the changes, we already have a watch established below, but see what it presents us with in terms of information. So it's going to give us, and we can see right away that it started with 3 and then jumped really quickly to 5, and we got a slight pause there, and then now we've got a few more old replicas pending termination, but pretty much we've got everything that we need rolled out already. So fairly quickly, because again, the application's lightweight, so it doesn't really need to pull it. Now if we look at the history, once this is all the way rolled out, right, it tells us it's rolled out, and we can look at the history for our deployment. Right, so the first rollout just says essentially none. The undo essentially says none because we didn't really record the undo, but that's our undo. And then there's our change. So we're back to the old application revision. So if we wanted to interrogate version 3, we could roll a history and then use revision 3. So one of the things to note, the record, as you saw in the command that we used, actually records an annotation for the change cause, but in the case of the undo, it just says none. So it doesn't mean there's no information available, it just didn't set an annotation. By interrogating it, we can actually see that the image changed as part of revision number 3, right? We did the undo. So it's still possible to get the change cause, it just in the change cause table, it just says none. So it does help to do some, to use the record flag in many cases. Okay, so that's just kind of the default behavior of rolling updates and interacting with them. There are a couple other features that we can leverage when it comes to rolling updates. Pausing. So we saw that once we introduced the change, it then immediately triggered the rollout, right? But a deployment's rollout trigger can actually be paused at any given time. So if you do it before any sort of change is introduced, then you can issue several commands to make different changes, and it won't trigger anything until you resume it. And then all the changes made prior to resuming are rolled out. Also in the middle, you can pause the rollout and do something like confirm settings before the whole thing completes. And so then in that case, resuming just simply finishes the rollout that was stopped in progress. Let's take a look at interacting that way. So we've got our various watches here. We're going to keep those established. But in this case, what we're going to do is first, we're going to pause. So we're going to pause the deployment so that changes that we make are not going to get pulled out, right? So let's introduce the Alpine revision again, right? In this case, we're again updating the version to Alpine, and we're going to see nothing happens, right? No rollout was triggered. Our client's still hitting the same the same revision. Let's introduce a second change, though, just to show that that's happening. So in this case, we're going to add CPU limit, right? So that will let us set resources for that for the container, right? In this case, the container called host info. Let's scroll up real quick and make sure that it was called host info. Yeah, so the name of the container here is host info. So this will let us set that. Again, nothing rolled out. Right, now if I introduce the resume, we should see all those changes roll out at once. Right, so we're going to get new containers again in the rollout, but not two rollouts, right? Because we introduced two changes, but because the rollout was paused, everything that was introduced before the resume was issued will be rolled out, right? So new, let's try a new pod. We'll do -o YAML, and we should be able to see resources. So we've got the resources that was not in our original manifest, right? Now, couple of ways that we can control rolling updates is through the max surge and max unavailable. So we have the default settings of 25%. But what if we change those things, right? The max surge is something that controls the number of pods in addition to the desired number that can be scheduled during a rolling update. This essentially allows us to break up the iterations into larger waves, right? We've seen in previous cases that there were a small number of pods, but we can break this up. A high surge percentage, however, is going to mean more resources, right? Because each application replica is going to need CPU and memory, and so you're going to just need more of those during the rollout. Max unavailable ensures that a minimum number of pods are always available, right? The idea being that we want to guarantee that that client traffic is delivered through pods throughout the rolling update. This cannot be 0. We have to have some value. And if you do set it at 100%, that's going to mean downtime, right? So let's try a couple scenarios using max surge and max unavailable. Okay, so I made a little edit there to expand the terminal a little bit so we can actually see a little bit more. So this first time around, what we're going to do is patch the max surge. What we should expect then is that we have a lot more pods that will get added on the rollout. So we'll introduce another change that should then see the behavior exhibit. So that's why I expanded the terminal here. So wow, we see a lot more pods roll out, right? So tons of pods get added immediately to the deployment so that we have a big surge of pods that get added to our cluster right away. Again, load balancing across many replicas in this case. And then we tear down a whole bunch of them because we've got a ton running, right? So you can tear down really quickly as well. Now let's do the opposite, where we're going to patch again, except for this time we're going to set max unavailable to 90% to see how that affects. Again, we should expect the opposite, where we don't have a lot of surge, but we have a lot of pods removed. Again, we'll introduce another change and see what happens there again. Hopefully that meets our expectations. So we've got a lot of containers terminating, but then also because we need to replace them, we've got a lot of containers that get created right away. And so in all the scenarios, we see that our client up in the upper right corner here is unaware of those changes across the board, again, because that's the benefit of the 0 downtime rolling updates. Okay, moving on to stateful sets. So stateful sets are intended to support stateful applications. These have some other features regarding stable network identities. So unlike deployment-based pods, stateful sets have unique ordinals so that we can actually communicate with individual members a little bit easier, and persistent storage. So there's an embedded PVC template that creates a persistent volume for each pod. Now, when we do the deletion, deleting a stateful set will delete the pods, but not the PVCs, because what we want to do is make sure that it wasn't a mistake, right? What if I accidentally deleted my stateful set and all my PVCs with it? Well, usually in the scenario where the persistent volumes are dynamically provisioned, the thing that keeps them from being returned to the storage pool is the binding between the PVC and the PV. So this allows us to make a deliberate decision when we want to delete the PVCs, making sure that if we accidentally deleted the StatefulSet, we don't have any data loss. The pod identities are tied to volumes. So failed pods are replaced by pods with identical identifiers, which means that existing volumes that were tied to a given pod replica easily bind back to that new pod that represents that same replica, right? So even though it's a new pod that's replaced the old one, it gets the same storage that the old pod had. Now, the ordinals give us some features: ordered or sequential deployments and scaling, right? So you can see here, we start with pod ordinal 0. Once it passes its readiness check, then we can move on to pod 1. Once it passes its readiness check, we move on to pod 2, and so on and so forth when we scale out for initial deployments, and then when we add more replicas. This allows us to have applications that communicate with each other as peers, right? So what's the point of a readiness check? It's to indicate when the application is ready to receive requests on the network. And so when we have peer-to-peer communication, we don't want to roll out a second replica until the first one is ready to communicate with it so that they can join consensus algorithms and things like that. No guarantee during termination, though. You can see at the bottom here, termination happens all at the same time. If you need an ordered termination, the workaround is just to scale to 0 first, and then delete the StatefulSet, and that will give you, again, it will tear down, scaling down from the highest ordinal down to 0. For rolling updates, pods are deleted and recreated or replaced on the same node. So unlike deployments where we're deploying applications, application replicas to potentially new workers, we're going to deploy a new version of the application to the exact same worker. This eliminates that need to detach and attach network volumes from the old node to the new node, right? That could be a heavyweight operation. Rolling updates will support the undo feature. So all of the imperatives we've been using with deployments and the status commands. The history is not super functional, unfortunately, and pause and resume is not supported at all. So it does have some overlap in terms of features for the imperatives, but not everything. And occasionally you may run into a scenario where you have to force a rollback. So the top section here is, again, just a repeat of the initial deployment, right? We go from 0 to 1 to 2 to n. And when we update, we start at n and work our way down, right? So we start at the highest ordinal, and the ordinal 0 would be the last replica to receive the update. So let's look at a scenario. First things first, let's get the storage classes. Just to show, we've got two storage classes. We've got the local storage, and then we've got an NFS client, which is the default storage class that we're going to use for the network attached storage scenario. In this case, we'll take a look at the StatefulSet. Although it's rather large, you'll see that the volume claim template isn't using a lot of data, and it doesn't have a storage class request, so it's just using the default storage class. There's a lot of logic here for starting it up and it being etcd. Again, what we want to do is establish a watch. So in this case, we're going to again use the label. So in this case, the app etcd net, which is the network attached storage version. So again, we're not going to find anything just yet. Let's go ahead and apply our StatefulSet. And we've got our service and our StatefulSet created. You're going to see the rollout, right? So initial rollout, we start with replica 0, and it'll go to 1 and up to 4. Now while that's going, I'm going to start a client over here again. In this case, we're going to just run etcd of the same version, but just call it etcd-ctl, and that's all we're going to use is the etcd-cuddle client here to run some things. So I'm going to export the correct version once the client gets up and running. Give that a moment. There we go. So we're going to export the etcd API version 3 and also export the endpoints. So we know that the endpoints are 0 through 4 in the service name. So we'll export those. And then I'm going to get a member list just to see that they're all up and running. We can see that one is just creating. So member list should give us a member list of 0 through 4 there. Now I'm going to put a value just to show that we can set and retrieve data. And then we'll start a loop. So in this loop, we're going to get the value that we set, and then also get the endpoint statuses to see the different versions that have been deployed. So we'll start that loop, and you'll see that the value, key and value are there, and then you've got the version, each one. So as we do a rollout, we'll get a sense of the version. So let's trigger the first update. So in this case, we're going to update it to just a minor revision and watch the rollout status. So what we'll see is it's, again, just like the deployment update in terms of the updates that we're getting from rollout status. But you can see the teardown happens from the ordinal 4 now onto ordinal 3, and we'll go all the way down to 0. Now what you'll see over here with the client is that we're going to get some error messages because certain endpoints are not going to give us their status. But what you'll see every single time is that we're still getting the data, right? Because the etcd application supports that the various members can still answer the query that we're sending them, right? We may not be able to query individual members for their status because they're in the middle of being down, but the data is always there, right? And that's the important part. And so as you see the clients answering over and over, they are giving us the data every single time, right? So we'll let that finish. I'm going to queue up an undo here just to, again, see how the undo compares between the StatefulSet controller and the deployment. So give that a moment to finish. Now we're on to the very last one. And it's up and running. So everything's been updated, right? And so the last 2 members here in the very last query from our client didn't answer. But now we're on to the fact that they're all answering again. And of course the data is still there. So let's go back, right? Something's wrong with this version, so let's roll it back again. So behavior again is the same, where we're tearing down from the highest ordinal down, which is what we expect, right? So in this case, I didn't ask for live update status. So let's take a look at the history as this thing rolls out, or reverts the change rather. So note that we did, on the first change, right, going back up here, we did record it. But as we said, the history is not very workable, or not very valuable. The second change, we didn't set a record. We did an undo and started to roll things back, but still didn't get anything. So again, if I want to interrogate a particular revision, right, I don't get a lot of information here. So the rollout history, not as robust as you would expect that we got from the deployment. We can even do partitioned updates because we have ordinals we can rely on. So initial deployment, again, is 0 to n. What we'll do here is set a partition and see that everything equal to or above that partition number will roll out with the new version, but the old pods will keep the old version. Now, even if someone comes along and deletes a given pod, it will stay the old version, even if it is deleted. So let's take a look at that. But what we're going to do is perform that with local storage volumes. And we still have the client running. We'll just make some changes to which endpoints it's connecting to. And we want to start a new watch with the new app etcd local key value pair. The only difference between the old network attached storage version, which uses the default storage class, and this new one is that it has the storage class name here, so that we definitely get the local storage class, which we see, if I can spell. We've got our watch established. Let's go ahead and deploy our application. And so now it's grabbed a local PV. So if I do kubectl get PV, we can see that we've got several being bound already, right? So our local storage volumes are getting used. Now again, we're going to export in our client some endpoints, but different names, right? STS local, and STS local is the service name. So I'll export those endpoints. And again, we'll do a put and get the same endpoints that we did before, or the endpoint statuses and the value, so we can see what happens over time. So now we want to introduce a change, but before we do that, we want to also introduce a partition number so that we update only some of them. So we'll patch the rolling update strategy so that it's partition. Actually, let's go with number 3. Right, that way we get a couple of replicas of the new version. Okay, so the StatefulSet is patched. Now let's introduce the change again, updating the minor version to .24, and witness the behavior that happens here. So again, we see that the version of Replica 4 changes, the version of Replica 3 is going to change, and then we stop, right? So we're going to see when the members start to report their values over here that the last 2 are 24 and the other 3 are 18. Now let's see if we delete a pod. So we'll come over here and delete STS local 1 because we know it's version 18. It's going to terminate that pod, and it should allow us to create a new one to replace it. And once the client catches up and can query all the endpoints once again, we'll see that the version remains 18, right? Even though it was deleted, the version comes back as the old version. Now, let's say I'm doing some sort of phased rollout and I'm happy with the phased rollout. Now I can update my partition to 0, and that will let me roll out the rest of that change. So we see that version 2 now updates itself. Version 1 is, or Replica 1, I should say, is now going to update itself. And then we'll see go all the way down to 0. So we see the entirety of the rolling updates happen. Right, so once we're done with our phased rollout, we everything updates, and now everything's up to 3.24. Once everything's up and running, again, our client throughout has availability to the data. That's what's important, right? We do have some errors communicated with individual members, but once they're back all up, right, we're all back to 3.2.24, and the data is available. So to sum up, we see that Kubernetes controllers provide features that do give us 0 downtime rolling updates, and behaviors differ by controller because applications are different, whether they're stateless or stateful. So hopefully that gives you a sense of how the StatefulSet and deployment controller behave in practice through some of the demos that we did today. Just wanted to pop in one more time and say thanks for your time.